Every day, humanity generates 2.5 quintillion bytes of text. News articles, medical records, legal documents, scientific papers. But here's the problem. It's all locked in sentences. Unstructured, unsearchable, invisible to machines. What if you could take any document and in seconds extract every person, organization, relationship, and event, automatically building a web of knowledge? This isn't science fiction. It's information extraction, and it's the technology behind Google's knowledge panel, medical diagnosis systems, and intelligence analysis. In this video, you'll see raw text transformed into structured knowledge, entity by entity, relation by relation. After this, you'll understand how machines read not just words, but meaning. Information extraction has evolved through 4 eras. In the 1990s, we wrote rules by hand, fragile patterns that broke on every new domain. Statistical models like CRFs brought probability in the 2000s. Then neural networks, BLSTMs, learned features automatically. But the real revolution came with transformers. Models like BERT don't just read left to right, they see the entire context at once. And that changed everything. Today's information extraction is a pipeline. Raw text enters. Named entities are identified. Relations between them are extracted. Events are detected. Pronouns are resolved. And at the end, a structured knowledge graph emerges. Let's build that pipeline piece by piece. Named entity recognition, NER, is the foundation. It finds and classifies the who, what, where, and when in any text. Watch. This sentence contains 5 entities hiding in plain sight. Apple, an organization. Tim Cook, a person. iPhone 16, a product. Cupertino, a location. September 12th, a date. Modern NER uses BIO tagging. Every word gets a label. B for beginning of an entity, I for inside, O for outside. BORG, IWARG, O BPR, IPR. This turns NER into a sequence labeling problem. State-of-the-art systems use a transformer encoder feeding into a CRF, conditional random field layer. The transformer captures deep context. The CRF ensures valid tag sequences. You can't have IPR after BORG. But here's where it gets challenging. What about New York University? New York is a location inside an organization name. Nested NER handles entities within entities. And it requires models that can think in layers, not just sequences. Modern NER doesn't just find names. It finds everything: money amounts, percentages, medical dosages, legal citations. Any structured fact hiding in unstructured text. NER tells you what exists. Relation extraction tells you how things connect. Tim Cook and Apple are both entities. But the sentence tells us more. Tim Cook is the CEO of Apple. Apple is headquartered in Cupertino. Apple manufactures the iPhone 16. Relation extraction finds these connections. Given 2 entities, what's their relationship? Modern systems use attention patterns between entity mentions to classify the relation type. But some relations span multiple sentences. Tim Cook joined Apple in 1998. He became CEO in 2011. The relation between Tim Cook and CEO only emerges across sentences. Document-level relation extraction handles this. But it's much harder. Then there's event detection. An event isn't just an entity. It's something that happens. The trigger word announced fires an event with roles. Who announced? Apple, the agent. What was announced? iPhone 16, the patient. When? September 12th. Where? Cupertino. Each event is a mini-structure with a trigger and arguments. Find the events, find the story. Now the missing links. Coreference resolution answers. When 2 expressions refer to the same thing. Dr. Sarah Chin published her groundbreaking paper. She demonstrated that the model outperformed its predecessors. The Stanford researcher's work was praised by her peers. Her, she, the Stanford researcher, her. They all refer to Dr. Sarah Chin. A coreference chain connects them. Without this, every pronoun is a dead end. Semantic role labeling goes even deeper. For every verb, it asks, who did what to whom, where, when, and how? The researcher analyzed the data with Python. Who, the researcher? Did what, analyzed? What, the data? How, with Python? Stack all these layers together. NER, relations, coreference, semantic roles, and you don't just have words anymore. You have understanding. Now comes the revelation. Watch everything work together. Raw text enters the pipeline. NER identifies entities. Relation extraction connects them. Coreference resolution links pronouns. Event detection captures what happened. And from the chaos of natural language, a knowledge graph crystallizes. This isn't theoretical. Google's knowledge graph contains over 500 billion facts, extracted from billions of documents using exactly these techniques. When you search, "Who is the CEO of Apple?" Google doesn't scan web pages in real time. It queries a pre-built knowledge graph. Medical systems use IE to build drug disease symptom networks, connecting a patient's records to treatment options in milliseconds. Intelligence agencies process millions of documents to map relationships between people, organizations, and events. But here's the twist nobody talks about. Take this sentence. The bank by the river collapsed after the flood. Is bank a financial institution or a riverbank? Did collapse mean a building fell or a business failed? You solved it instantly. Machines? They struggle. And when NER gets it wrong, the error cascades. A misidentified entity creates a false relation. A false relation spawns a phantom event. One mistake at the bottom corrupts the entire knowledge graph. This is why information extraction is still one of the hardest problems in NLP. 80 years of research, and ambiguity remains undefeated. So what does this mean for you? The modern information extraction stack is built on transformers. BERT or similar models provide the foundation, deep contextual understanding. You fine-tune for each task: NER, relation extraction, coreference, event detection. Then you integrate them into a pipeline. And the output? A knowledge graph that makes unstructured text searchable, queryable, and actionable. In healthcare, IE extracts drug interactions from millions of research papers, catching combinations that no human could review. In legal tech, it analyzes contracts to find risky clauses in seconds. In finance, it monitors news to detect market-moving events before they trend. The key insight: information extraction is the bridge between human language and machine-readable knowledge. Without it, AI can generate text, but it can't truly understand documents. Welcome to Unit 3, Advanced NLP Techniques. This is where the fundamentals from Units 1 and 2 become superpowers. Over the next 6 videos, you'll master information extraction. That's today. Document-level NLP. Few-shot and zero-shot learning. Advanced prompting. Model compression. And real-world applications. If you're building AI systems that need to understand text, not just process it, this unit is your blueprint. Hit subscribe so you don't miss a single one. From text to knowledge. Let's build.